So chapter 8 is all about chemical equations, and we're going to begin by defining what we mean by a chemical equation. So in a chemical change or chemical reaction, one or more new substances are formed. So we're always going to have forming what we call the products. So the products are going to be different from the things they're made of, which are called the reactants. So sometimes the reactants are referred to as the starting materials. So yeah, that's basically it. We're going to take some starting materials, which we call the reactants, and they're going to be converted by this process called the chemical reaction into the products. And in the products, there's going to be a different arrangement of how the atoms are connected to one another. So they're going to be what we call new substances. Now, typically when a chemical change or a chemical reaction occurs, there'll also be physical changes. So we'll see things like changes in color or changes in physical state. And there also will be changes in energy. So we might find that energy is released and will get hot, or alternatively we could find that energy is absorbed and will get cold. An important property of chemical reactions is that there is no change in the amount of matter present. So if I start with 10 grams of things, I'm going to end up with 10 grams of things. So the mass of the reactants that I start with is always equal to the mass of the products that I end with. So what we can say is that in a chemical reaction, mass is neither created or destroyed. And so this is referred to as the law of conservation of mass. Now, if we put this together with Dalton's postulates that say that an atom of one type cannot be converted into an atom of another type, we could reformulate the law of conservation of mass as saying that in a chemical reaction, the number of atoms of each type is constant. So if I start with 4 carbon atoms, 4 oxygen atoms, and 2 hydrogen atoms, then at the end of my chemical reaction, I will still have 4 carbon atoms, 4 oxygen atoms, and 2 hydrogen atoms. They're just going to be connected to each other in a different manner. So if we go back and think about how we use symbolism in chemistry, we might say that element symbols are kind of like the letters in English language, and chemical formulas, which are small collections of element symbols, are kind of like words in English language. And then if we put symbols and formulas together to describe a process, that's kind of like putting letters and words together to describe an event. So chemical equations are what we get when we put symbols and formulas together, and they're kind of like sentences. So it's important to define what we mean by a chemical equation. So a chemical equation is a statement using chemical formulas and atomic symbols that expresses both the identities and quantities of the things that are involved in a chemical or a physical change. And when the correct quantities of things are described, we say that our chemical equation is balanced, because between the reactants and the products, we're going to have the same number of each type of atom. So it's kind of balanced, right? It's got the same number of every type of atom in both the reactants and the products. So we write an equation with the reactants on the left, separated from the products, which are written on the right, by an arrow. And if you have more than one reactant or product, you're going to write those guys separated by a plus sign. So in this reaction, we've got 2 reactants giving 1 product, just written out symbolically. But here's a real example. We've got reactant 1, reactant 2, hydrochloric acid, sodium hydroxide, reacting to give sodium chloride and water. So these guys are the products, and these guys are the reactants. And as I mentioned previously, sometimes they're referred to as the starting materials. Okay, it can be very important sometimes to put what we call physical state symbols, and we do that by indicating the physical state in parentheses with the symbol either S, L, or G following the formula of the compound. So this could be read as solid carbon reacts with gaseous oxygen to produce gaseous carbon dioxide. So that's how we would read that. Another common symbol that we'll see that indicates the physical form of a substance is to write AQ in parentheses following its formula, and that indicates that the substance is dissolved in water, that it is an aqueous solution. So an aqueous solution just means that it is dissolved in water. Aqua is Latin root for water. So this is saying that a solution of hydrochloric acid is combined with a solution of aqueous sodium hydroxide to give a solution of sodium chloride and water. So coefficients are numbers that are placed in front of formulas or atomic symbols to indicate how many units of each substance are present. And if we have the correct coefficients, then our chemical equation will be balanced and have the same number of atoms on each side. So this first chemical equation here is not balanced because you can see that on the left we have 2 hydrogen atoms, on the right we have 2 hydrogen atoms, on the left we have 2 oxygen atoms, but on the right we have only 1. So we need to balance this chemical equation by adding one or more coefficients that are placed in front of the formulas. So this chemical equation here is balanced because on the left we have 2 times 2, 4 hydrogen atoms. On the right we have 4 hydrogen atoms. On the left we have 2 oxygen atoms, and on the right we also have 2 oxygen atoms. So this guy is good. This guy, no good, not balanced. You always have to be very careful in looking for that word balanced. If an equation isn't balanced, you need to make it balanced by adding coefficients. If you're asked to write an equation, you need to make certain that it's balanced by having the correct coefficients. So we balance the atoms in a chemical equation by placing coefficients in front of their formulas, and that's the only way of balancing a chemical reaction. So this chemical equation up here is not balanced because while we have 1 carbon on both the left and the right, when we look at the hydrogens, we have 4 on the left and we have only 2 on the right. And if we look at the oxygens, you can see that we have 2 on the left, but we have only 1 on the right. So in order to bring this into that's not correct, is it? We don't have only the 1 oxygen on the right, but we have 3. There we go. So in order to get this to balance, what I'm going to need to do is add a 2 in front of the hydrogen, in front of the water here, to get up to 4 hydrogens. So multiply that by 2, and then I'm going to add a 2 over here, and then that'll get that up to 4. And now when I look there, my oxygen's now balanced because I've got 2 times 2 on the left, and I've got 2 times 2 on the right. So I've got 4 oxygens on both the left and the right, and then the hydrogens that didn't balance before, I've now got 4 on the left and 4 on the right. So that's all good. Okay, so you get the idea. Now we'll go through some generalized procedures to help you with this. Now something that's very important is when you balance a chemical equation is that you never change formula subscripts. That's not appropriate. The only way you can balance a chemical equation is by adjusting coefficients that are in the front of your formulas. Similarly, you can't just add random substances in to get your chemical equation to balance. We don't do that. We just change one or more of the coefficients. Now, when you go through, you might find that the set of coefficients you have is not the smallest whole number possible. It could be either too big or it might not be a whole number. So what we always do is after we've balanced, we have a look to see if we can either divide through by a common multiple or multiply it by a whole number to get all of the coefficients as being the smallest whole number possible. So if my attempt at balancing led me to something like this, I should check to see whether I can divide through by a common multiple, which I can. In this case, I can divide through by 2, and then I would get the better set of coefficients, and that's what I'd give for my balanced equation. So a properly balanced equation has the smallest whole number set of coefficients. So let's have a look at a problem. So it says solid potassium. So potassium has the symbol K, there it is, and chlorine gas. Now you have to remember your diatomic elements, right? So it's the have no fear of ice cold beer elements. There's 7 of them. Okay, so 6 of them are over there, and then it's hydrogen. So that means that chlorine gas is CO2G. React to produce solid potassium chloride. So this is the reaction between a metal and a non-metal. So potassium chloride is going to be an ionic compound. So potassium's in group 1A, so it is +1, and then chlorine is in group 7A, so it's -1. So these guys are going to combine 1 to 1, and that's a solid. Now it doesn't balance because you can see immediately that I've got 2 chlorines on the left and only 1 on the right. So I need 2 there. But when I do that, now my potassiums don't balance because I've got 1 on the left and 2 on the right. So I'm going to need a 2 there. And now everything balances. Okay, so I have 2 potassiums on the left, 2 potassiums on the right, 2 chlorines on the left, and 2 chlorines on the right. So everything is looking great. Okay, so as I said, you always want to keep an eye out for that word balanced. That's really important. And the fact that they're giving you these phase labels here all the way through is a good sign that it's really important to include them. Okay, so that brings to an end this small section on the chemical equation. In the next section, we're going to look a little bit closer at how to balance chemical equations when they get a bit complicated and have what we call interfering coefficients. All right, good luck with everything, and yeah, let me know if you have any trouble.